Okay. So, we have already started characterizing random process, right. We have said how to evaluate mean and autocorrelation function, means how to characterize random process first of all, and then why we need at different time instance and their means correlation. That is something we have already talked about, and then we have started talking about evaluation of mean and autocorrelation function, right. So, these two things we have already done. Now, for the higher order, what we will have to do is definitely we will have to evaluate this P x at let us say nth one. So, we have to do this joint distribution at different time instance, and then multiply this with x 1, x 2, x 3 up to x n and do nth order integration, and you will get the nth order autocorrelation, okay, or correlation I should say. Okay. So, this is something we can keep on doing for any value of n. But now what will be interesting for us, let us try to see those signals, the signals that will be interesting for us, for which we can do some analysis. The signal that will be interesting, so suppose a signal is going on, okay. If the statistical property of the signal basically depends on which time I observe, then I have a signal which is very hard to characterize, because the signal statistics is keep on varying. It is not just the signal, signal is keep on varying, that is all true, but now we are talking about the statistical property of the signal. If that also keeps on varying, then I have almost nothing to, means no hope to at least analyze that signal. So, now we will be talking about a class of signal where the signal might vary in time, but the statistical property probably does not vary with time, which is means defined as stationary process. So, we will now try to define the stationary process. Okay, so, this is something we will try to define. So, I have told a stationary process will be, or a stationary random process will be, whose statistical property does not change over time. Okay. What does that mean? That means all those PDF and joint PDF we are defining, they are not really dependent on the time where I start. Okay. So, let us talk about that mean first. So, mean was, my mean x t bar was something like minus infinity plus infinity x p x x t dx, right. So, this was my mean. Now, this PDF, if irrespective of any time t, it is same. Okay. That means, any time you sample, I have talked about that noise signal, I have told that probably the PDF at every sample instance gives me the similar PDF. That was the first insight of a stationary process, that okay, this is what happens generally in most of the signals that we study, most of the time it will probably be stationary. Okay. If there are no other influence, time varying influences in the signal. Okay. We will see that again we will differ from this, and we will say most of the realistic signal are not stationary, okay, because it comes through the channel and channel keeps on varying over time. But for the time being, let us say that most of the signals that we observe are stationary. What does that mean? That every instance you take associated PDF, that means like that experiment we were saying, that multiple students will be there, will sample it and they will be recording the current. We will sample it at particular time, let us say 12 o'clock in the noon, and we will say okay, give me whatever sample you have got. We plot the histogram, get the PDF, normalize it, get the PDF, that is fine, one part. Then we say okay, 1 o'clock whatever you have observed, give me that. Again we do the histogram, plot and normalize it, get the PDF. We will see that those two PDF will be identical, and any time we take that, probably all of them will be identical. Okay. That is the time when we would say that mean is irrespective of time, it will be just x bar, because if the PDF is same and the signal value, because the PDF is same, so therefore its mean, because PDF characterizes mean, right. So, its mean also will be same irrespective of whatever time you take. If the PDF is stationary over time, the mean value also will be stationary over time, it is not going to change. So, that is the insight we will get, that first order it is stationary if at every time instance the PDF is that single PDF. Of course, we are just taking that at that time instance the sample and talking about this. So, if this is happening, then we can say first order it is stationary. Okay. Next the second order comes. Now, what we do, we actually take the joint PDF with 2 samples or 2 time instance, okay, and then again do the histogram plotting with normalization, try to see what is the joint PDF. If the joint PDF again remains stationary for any 2 time instance we take, but remember the time separation has to be same. Okay. So, because I am taking a joint PDF and I have just said the statistical property should not be dependent on the first time instance I take or the origin of my calculation. Okay. But that does not mean any time I take, because any time I take the means nature of dependency will be varying. Just a simple low pass filtering will tell you that. If you take it closer enough, the variation that it can take, means suppose I have a signal, it is a low pass signal. So, from here whatever value it has taken, if I take a very closer time instance, it will have a lower variation, but if I go further away it will have a higher variation. Okay. So, therefore, the time separation between 2 points I am considering, that is very important, that has to be there, that is a fundamental characteristics of the signal. But where from I start, whether I take this and this or this and this, it should be independent of that. So, if I can now say that the autocorrelation function which we have defined, which is the second order thing, right. So, which is that Rx T1 T2. It was earlier a function of T1 and T2. Now, if I can say that this is only dependent on the separation between them, not individual values. Okay. So, if I can say this is just Rx T2 minus T1, it just depends on the separation of them, but not where the T1 is. So, T1 can be anywhere, but if you keep the same separation, you can put T1 at anywhere, whatever statistical property you will be getting, it remains the same. Then we can say at the second order also the function or whatever random process we are taking, its statistical property remains stationary, and so on. If I go to the suppose nth order, then I should specify that Px, this x1, x2 up to xn the way we have specified in time t1, t2, tn must be equal to, now again the differences, right, that should be same. So, therefore, I should be able to say that it should be x1, x2, xn at time I can specify, let us say T2 minus T1, T3 minus T1, Tn minus T1. Okay. So, wherever the T1 is, just as long as T1 to T2, T1 to T3, T1 to T4 are all same, I can shift the whole thing, take the whole statistics, it will remain the same. Then I can say at the nth order also it is stationary. Okay. So, first order, second order, like that nth order up to infinite order, whatever order you can go. If you can say all of them are remaining stationary, that means it does not depend on the origin, then the whole signal has the statistical property which is stationary, and that is a very strong condition. We call those kind of signal as stationary, or those kind of associated process, which is a combination of those signals. Associated, that process is called a stationary random process. So, that is the definition of stationary random process. But as you have seen that stationarity of a random process, proving that is going to be a daunting task. So, what we will do, we will be happy with just 2 order. So, people are happy with 2 order. We just say that x bar t is just x bar, does not depend on time, and Rx T1 comma T2 is just dependent on the separation of them. If this happens, then in the first order and second order they are stationary. All other higher orders we do not test, we just say it is a wide sense stationary process. Of course, it is a weaker condition, or we say generally say weak stationary process. Okay. So, that means first and second order we have tested, it is just our limitation of computation. Okay. So, we have tested first and second order, we have seen that it is stationary, we do not go means wish to go to higher order, because that is too complicated to check. So, we just declare probably first and second order it is already stationary, and you will see all the signal processing that will be done will mostly dependent on this first two order statistics. It does not go any higher. Okay. They are important, but you will see for all our calculation probably it is not going any higher order up to any higher order statistics. So, up to this if they are stationary, we can say that we can just assume them to be stationary, and we call them wide sense stationary. Most of the signal that we will be dealing with will be means we will assume that they are wide sense stationary, because you will later on see that if they are not wide sense stationary, there is no analysis, because if the statistical property also varies with time, I have no hope of any analysis. If they are stationary, that means statistical properties are fixed, then I have some average sense of analysis for these random signals as well, okay, which will be eventually used for our noise analysis and any random reception analysis. Okay. So far I hope this is clear what we mean by stationary and wide sense stationary. Okay. Now, we will just try to give one example. Okay. So, just an example where you will be able to see that a particular signal means all these concepts we have told that will be captured. Okay. So, let us say I have a signal which is actually A cos omega c t plus theta. Okay. So, this is a usual cosinusoidal signal with a phase, frequency and amplitude. Now, we are just adding some more things to make it random. This A is fixed, amplitude does not vary with time, okay, or it does not vary over signals. This omega c is fixed, frequency is fixed, but this theta might vary and vary in a random fashion. So, the theta has a PDF of means it is uniformly distributed between 0 to 2 pi. So, because PDF has to be integrated to 1, so the strength should be 1 by 2 pi, right. So, that is the PDF of theta, that is theta, right. So, this is something I know. So, what will be happening associated with that, there will be multiple random signals now will be generated. So, if I just try to see, one possibility is it has a 0 phase, right. So, if it is 0, it will be just a pure cosinusoidal signal. The other possibility has it has some phase, so that with that lag the cosinusoidal will be starting. So, there will be infinite such phases between 0 to 2 pi, and all those signals are those random signals that we were talking about. Of course, their amplitude is not changing, but it is the phase they are changing randomly. So, all those sample signals, so even when theta is probably pi by 2, then immediately it becomes sine. So, it will be something like this. Okay. So, this and this two are valid signal generated from the same process, same random process, only when the theta varies. So, theta is 0 over here, theta is pi by 2 over here, okay, and so on up to 2 pi it can. So, it can take any of these are all, they are actually 1 random signal, any of them might be chosen, because when I am transmitting I do not know that theta, what that theta will be at the receiver side. So, any of them will be chosen for me. Now, what I wish to do is I wish to see whether this particular process is that a stationary process or is that a wide sense stationary process. So, this is something I would like to evaluate. Okay. So, I would like to see that theta with this PDF of theta given, will this be in time if I wish to see is this a stationary process? So, let us first evaluate the average value of that, right. So, let us say I wish to do this, that should be A cos omega c t plus theta average. Remember, whenever we are talking about average, so far we have been in signal, we are talking about average in time, right. This is not average in time, this is on that random variable. Okay. So, if I wish to do that average, it is again a functional average of that theta. We have done that already. So, what is that? That is actually this function multiplied PDF of that random variable integrated over that range of that PDF, right. So, PDF is ranged, I have seen already, it is ranged over 0 to 2 pi, right. So, it should be integrated from 0 to 2 pi A cos omega c t plus theta, that is a functional average, remember, into PDF of theta, which is 1 by 2 pi within this range d theta. So, that should be the evaluation. It is not time average, remember that. We will come to time average later on, we will be defining another subclass of process. Okay. So, A is a constant 0 to 2 pi, 1 by 2 pi goes out. So, it is just A cos omega c t plus theta d theta. So, if I just do this from 0 to 2 pi, you will see that this will be 0, because we are integrating cos, okay, from 0 to 2 pi, right. So, theta varies from 0 to 2 pi, any cosinusoidal signal within a particular period, if you integrate, that should be 0. So, this is 0. The good part that has happened is I have started with any t, remember that t was there. So, it can be any t, but for any t I could now prove that this is 0. This will be 0 for any value of t. So, that must be constant over time, that is the good part. So, it has a mean value of 0 at every time instance. So, that means first order I can say this is stationary. This is the statistical property, remember I am doing ensemble average, and the ensemble average is giving me a constant value, right, for this signal. It does not depend on time. So, the average value of this signal does not depend on time. So, that is the first step towards telling that it might be a stationary process. Now, we have to do for the second one. So, for the second one, what we have to do is something like this. We have to evaluate Rx, T1, T2. So, at value of T1 I will be taking a value of this particular signal, and T2 will be taking a value of that signal, and then we have to do ensemble average over the variation of whatever random variation we have, that theta. So, this must be A cos omega c T1 plus theta into A cos omega c T2 plus theta average. This is ensemble average. What is the variation? It is just theta variation. So, average again will be a functional average. So, over theta random variable. So, this must be A square is there, integration 0 to 2 pi, PDF of that is 1 by 2 pi d theta, and into this function which is cos omega c T1 plus theta into cos omega c T2 plus theta, right. This is the one. I can take out, so A square by 2 1 by 2 pi comes out 0 to 2 pi. So, now this will be 2 cos A plus A into cos B. So, I can write that as cos omega c, this minus this theta gets cancelled. So, that will be T2 minus T1 and plus cos omega c. So, this plus this, so which should be omega c T1 plus T2 plus 2 theta, right. So, this whole thing d theta, right. So, we are just doing the ensemble average, nothing else. So, A square by 2, the first term, that is not dependent on theta. So, therefore, the first term if you integrate will be distributed, of course. First term if you integrate, just that thing comes out, 0 to 2 pi d theta will be integrated. So, that will be 2 pi, this 2 pi gets cancelled. So, I just get cos omega c T2 minus T1, right. The second term, it will be this cos something which is not a theta variable 2 theta integrated over 0 to 2 pi. Again, because it is cos and going through one period, so it will just be cancelled, whether it is whatever it is, it will be just cancelled out, cos positive half and negative half will cancel each other. So, this integration will always be 0. So, that part will be 0 whatever happens. So, now let us see what has happened to my Rx T1 T2. Is this separately dependent on T1 T2? No, it is just dependent on the separation. So, immediately I can see it is actually just dependent on the separation, nothing else. So, I can now say in the second order also it is stationary, because my definition of stationarity was that in the second order it has to be just dependent on the difference of it, nothing else, okay. And so on, you can keep doing that and you will be able to prove that it is stationary at every order, okay. But probably will be happy content with this. You can test for higher order also, but we will be happy with this, because up to 2 order we already have a strong condition. We can say this is wide sense stationary already. So, that particular function we have chosen, fortunately, even though theta has a random variability, we could see a random process which is stationary over time. So, its autocorrelation function is dependent on just the separation of those 2 time instants whatever you take, okay, and its mean is constant, it does not vary over time, okay. So, immediately we can declare, okay, this is probably a random process which is stationary. Now, we will talk about something else which is called the ergodic . Okay. So, what do we mean by ergodicity? Let us now try to talk about that. We have already talked about the stationarity. Now, what we do, we will pick one of the sample. Instead of taking all of them, we will pick randomly one of the sample, any one of them is good, okay. So, there is no preference for that, any one of the sample we will pick, and we will try to do the same thing in time, the averaging and second order statistics, means statistics, here it will not be statistics, it is the second order autocorrelation function, the way we have defined autocorrelation function, okay, in the previous previous few classes, right. So, let us try to do that. So, first is the average. So, we say this is that was ensemble average, this is time average. So, time average is nothing but this, which is limit t tends to infinity, because it is a periodic signal. So, if this is a periodic signal, then I can just talk about time average as if I take it for a big period, do the average and make the period stretch to infinity. So, 1 by t minus t by 2 to plus t by 2 x t dt. Okay. So, this is the time average. So, over the entire time duration you pick all the samples, and then means you cannot pick samples here because it is continuous. So, you integrate it and divide by t, because for t time duration you have integrated. If t is stretched to infinity, then you get for the entire sample, okay, or entire signal. So, that is the average. Remember what we are doing for the ensemble, we are taking a single time and we are taking multiple samples, we are doing ensemble average. Everywhere we are picking a value and we are doing average of them. So, that is called the ensemble average. Here what we are doing, among all those sample signal, we have picked one of the signal, no preference for it, any signal will do. Take that signal and do over time averaging for that entire signal. You do not consider any other signals, just that signal, do a time average, you get this, okay. And the autocorrelation, the way we have defined autocorrelation. So, Rx tau will be defined as xt and xt plus tau, and then we do time average, which is similar, limit t tends to infinity 1 by t integration minus t by 2 to plus t by 2 xt xt plus tau. This is how we defined autocorrelation function in time domain, right. So, if I evaluate this one, then I get the autocorrelation. Now, if for me or for a particular sample space If this happens that any sample I pick, I evaluate these two things and they are exactly equal as the one we have got for the stationary process. If this happens, then the associated random process is called a ergodic random process. Okay. So, ergodicity means that whether you do it in ensemble or you pick a sample, any sample it will do, and do it in time, both the things will give you same result. Okay. So, as long as that is happening, then we can say that this process, underlying process, is probably a ergodic process. Okay. What I would request you, means I will not do that because it is a very simple one, simple exercise. I would request you to just test the sample we have taken, take any theta, okay, that A cos omega c t plus theta. Here a particular sample means any theta you can pick. Out of those random 0 to 2 pi any value, you can pick any of them. It does not have any preference, that also will be clear to you. So, pick any of them, either 0 or pi or 2 pi or pi by 2 or pi by 4, whichever value you pick, you will be able to show that the time average if you calculate, because here the time average will be just if you do it within a single period, because it will be just repeated. So, you do not have to do it for the entire thing because it is a periodic signal. So, you just have to do it over a period, and over a period if you just do time average as well as autocorrelation function, they will be same as what you have calculated, the same value will be coming out. Okay. So, this is something you will be able to prove, and then you can show that the signal we have picked, that is why we have picked that signal, that is a ergodic signal as well. Okay. Or we should say wide sense ergodic, because we are not proven for higher order statistics, we are not going to order 3 or order 4 and so on, okay, because that will be too much. So, at least up to second order you can prove that it is stationary, and then finally you will be able to prove that it is also ergodic. That means, any sample, any theta you pick, it will give you same result. So, that is the strong condition for most of the considered signal, probably you will see, and many things can be proven for these kind of signals, either it has to be stationary or it has to be even more stringent, that it is ergodic. Okay. So, I will just, before ending this class, I will just give you one very simple example of ergodicity, probably that will give you some idea of ergodicity. This is again an example picked from the book we are following. So, suppose we have a Manhattan street kind of configuration, okay, and you have all those southeast and northwest, north south and east west, these streets are there exactly perpendicular to each other. Okay. So, every street has crossing. Okay. Now, we say that every that crossing whatever signal that are there, with 75% chance that that can be green and 25% chance is there that can be red. Okay. Now, let us try to do this experiment, that a particular car going from this to this over a particular street going from south to north, okay, it will be crossing multiple these things, multiple signals, and then what he has to see is, and we also assume that all these signals are independent of each other, okay, they are not correlated, that if this is green that will be also green with this probability and all those things, they are completely independent of each other. So, if I just see one driver who is going from north to south and crossing multiple such signals, okay, and then try to evaluate how many times he will be, or how many out of all those signals he has encountered, how many signals he will be observing as red and how many signals he will be observing as green. That should be exactly from our definition, we know that 75% of the chance or 75% of the signals he has encountered probably will be green and 25% of them will be red. So, I can immediately see from that driver's point of view, and that driver can be any driver. Now, let us say multiple drivers are flocking around. Okay. So, they are actually coming to a particular signal. How many of them will actually report that I have seen green in that particular one, and how many of them will say that I have seen red in that, because it is 75% and because the drivers are coming at any time. Okay. So, because it is 75% times it is remaining green and 25% times it is remaining red. So, probably you will see that out of all those drivers 75% will report that at that particular signal point I have seen green, and 25% of them will report that I have seen red. So, what is happening, out of all those drivers one of them you picked and you actually went through time, because whenever he is driving at different time different signal he is observing, and he is reporting whatever he is reporting, that PDF is exactly true for if you just sample it over a particular signal, as if that a single, in our definition, single time instance. Okay. So, single signal is single time instance and multiple signals are different time instance. So, a particular means signal, if it is going, means particular driver going through it, that means it is over time going through, and whatever average value he is observing, that is becoming same as if you take more, means more number of drivers in a particular signal point. So, this particular scenario is actually a ergodic process, because for any driver you pick they will report the same thing. Okay. So, this just demonstrate which are the processes that can be ergodic and what is the meaning of ergodicity, right. So, with that probably we will end this particular class, and then we will try to show you if a signal is stationary, what can we do with that, okay. What is the advantage we get if a stationary signal is there, okay, in the next class. Thank you.